Acid-base equilibrium. Introduction to acid-base titration curves. In this tutorial, we will be going over a general overview of titration curves, acid-base indicators, titration of a strong acid with a strong base, titration of a strong base with a strong acid, and calculations involving the titration of a strong acid with a strong base. General overview of titration curves. Acid-base titration. A titration involves the slow addition of a titrant to an analyte. A solution containing a known concentration of acid or base is slowly added to an unknown concentration of acid or base. As you can see here, this is the general setup that we would use in a lab situation. Titrant. A titrant is a solution of known concentration that is added to the analyte. This also may be known as the titrator, the reagent, or the standard solution. This solution is found in the burette. An analyte is a solution of unknown concentration that is being identified and measured. This solution is held in a beaker or an Erlenmeyer flask. An indicator is added to the analyte to indicate the endpoint where a color change is observed. Acid-base indicator. Acid-base indicators can be used to signal the endpoint of a titration. Acid-base indicators are substances that exhibit different properties like color in their protonated, which means they have a hydrogen ion, and deprotonated, the lack of a hydrogen ion, states, making that property respond to the pH of a solution. An acid-base indicator can be used to determine the pH of the analyte, just as they can be used to indicate the endpoint in a titration. A variety of indicators change color at various pH levels. A properly selected acid-base indicator can be used to visually indicate the approximate pH of a sample. An indicator is usually a weak organic acid or base dye that changes colors at definite pH values. The weak acid form, HIN, will have one color, and the conjugate base, IN, will have a different color. The weak acid equilibrium is HIN, ionizes to form hydrogen ions and the conjugate base. pH titration curve. A pH titration curve is a graph of the pH as a function of the volume of the added titrant. Equivalence point. The equivalence point is where the mole values of the acid and base are equal, typically used to determine either the molarity of the acid or base or the volume of the acid or base required to reach the equivalence point. The pH is determined by either the conjugate acid or conjugate base that is formed. This occurs before the endpoint, where we see an indicator color change. Titration of a strong acid with a strong base. For the titration of a strong acid with a strong base, hydrogen ion concentration is in excess before the equivalence point, and hydroxide ion concentration is in excess after the equivalence point. Important points. Prior to the addition of base, the titrant, the pH is low. In other words, the pH is around 1, as we see right here. As strong base is added, the pH increases slightly, as we can see in the gentle rise of the graph right here. The pH changes very quickly near the equivalence point, as the hydrogen ion concentration equals the hydroxide ion concentration. So we can see this highlighted green area where hydrogen and hydroxide ion concentrations are equal. Equivalence occurs at pH 7, as we can see represented by this dot right here. Continued additions of strong base is shown by the flattening of the top of the graph, where the pH is in between 11 and 12. So we see that point right here on our graph. For the titration of a strong base with a strong acid, the hydroxide ion concentration is in excess before the equivalence point, and the hydrogen ion concentration is in excess after the equivalence point. Important points. Prior to the addition of the acid, the titrant, the pH is high, pH around 13, as we can see here on our graph. As strong acid is added, the pH decreases slightly, as we can see here by the gentle slope of the graph. The pH changes very quickly near the equivalence point as the hydrogen ion concentration equals the hydroxide ion concentration. Again, we can see this in our highlighted green area on our graph where hydrogen and hydroxide concentrations are equal to each other. Equivalence occurs at pH 7. Again, we have that point here on our graph. And continued addition of strong acid is shown by the flattening of the bottom of the graph around pH of 1. The hydrogen ion concentration is in excess down here at the bottom of the graph. Calculations involving the titration of a strong acid with a strong base. Neutralization between a strong acid and a strong base occurs when the number of moles of hydrogen ions from the strong acid equals the number of moles of hydroxide ions from the strong base. The point at which this occurs on a graph, again, is known as the equivalence point. The general formula that we'll use here is MAVA is equal to MBVB, where MA is equal to the molarity of the acid, VA is equal to the volume of the acid, MB is the molarity of the base, and VB is equal to the volume of the base. We know from the molarity formula that if we multiply the molarity times volume, we will get moles. So this formula provides us an opportunity to compare the moles of acid to the moles of base. Important points to remember. Pay attention to the acid to base mole ratio. If the acid to base ratio is not 1:1, then the formula will need to be adjusted to reflect the mole ratio. Given the reaction HClO4, which is a strong acid, plus LiOH, which is a strong base, produces LiClO4 and water. This equation is balanced. Consider the titration of 25 milliliters of 0.100 molar HClO4 with 0.300 molar LiOH. Determine the volume of strong base required to reach the equivalence point. So when we look at this stimulus, we know that the volume of acid is 25 milliliters. The molarity of the acid is 0.100 molar, and the molarity of the base is 0.300 molar. The volume of base is our unknown. So we'll start with our general formula of MAVA is equal to MBVB, and looking at the mole ratio of hydrogen to hydroxide, that's in a 1:1 mole ratio, so we do not need to adjust our formula. We will rearrange this formula to solve for the volume of base. The next step is to give the numbers that were given to us in the stimulus and plug them into our formula. When we perform the calculation, the volume of base is equal to 8.33 milliliters to the correct number of significant figures. Unless otherwise indicated, we can keep this as milliliters unless the stimulus tells us to convert it into liters. Let's look at another example. Given the reaction, 2HNO3 plus BaOH2 yields BaNO32 and 2H2O. This equation is balanced. Consider the titration of 200 milliliters of an unknown molarity of HNO3 with 25 milliliters of 2.0 molar BaOH2. Determine the molarity of the strong acid required to reach the equivalence point. So we are given a volume of acid of 200 milliliters, a volume of base of 25 milliliters, and a molarity of base of 2.0 molar. Our unknown is the molarity of the acid. To understand how this mole ratio will impact our formula, we need to look at how many hydrogen ions and hydroxide ions are produced in solution. So we know that 1 mole of HNO3 will ionize to form 1 mole of hydrogen ions and 1 mole of nitrate ions. BaOH2 will dissociate to form 1 mole of Ba plus 2 ions and 2 moles of hydroxide ions. So when this reaction occurs, we will have 1 mole of hydrogen ions and 2 moles of hydroxide ions in solution. We need to take that into consideration when doing our calculations. So the general formula here is MAVA is equal to MBVB, and we're going to put a 2 on the base side of this formula to say that there is a 1:2 ratio of hydrogen ions to hydroxide ions in solution. We'll rearrange our formula to solve for the molarity of the acid. Then we'll plug in our values from the stimulus. So MA is equal to 2.0 molar times 25 milliliters times 2 divided by 200 milliliters. When we do our calculations, the molarity of the acid is 0.50 molar to the correct number of significant figures. Paying attention to that mole ratio is very, very important. So what did you learn? We did a general overview of titration curves. We talked about acid-base indicators, the titration of a strong acid with a strong base, the titration of a strong base with a strong acid, and then finally calculations involving the titration of a strong acid with a strong base. Need more help? Feel free to contact me. Have a great day.